Welcome back. Today we are going to be going through lesson 5.1, which is all about solving systems of equations by graphing. So much of this is going to be review from Algebra 1, but we also are going to add in some things for Algebra 2 with quadratics. So let's start by reminding ourselves just what is a system of equations. So a system of equations is two or more equations with the same variables. So we have an example there. Our first equation is y equals x minus 1. Our second equation is y equal x squared minus 5x plus 4. So that's a system of equations, two or more equations with the same variables in them. So to find solutions to this, we are looking for an ordered pair, an xy pair, that's a solution to both systems in the equation. So we're looking for one coordinate pair that is a solution to each equation in the system. So if we plug in an x value to each equation, we want to see that we get the same y value out for both equations. Today we're going to be focusing on graphing those. So here are our first two examples. In these two examples, we are given the graph with the systems. If these are the two equations, they're graphed there on the coordinate plane, and we are looking for the point that satisfies both equations. A point that satisfies both equations is where they're the same. Both lines are at the same point. In this case, that would be that point right there where they intersect, and that is the point 1, 7. To check our work, we would plug in that ordered pair to see if it works. So for A, if I plugged in the point A, 0, 1, I would have y equals negative 3 times the x plus 10, and I would see that 1 equals 10, and that is not true. So that's how we know that first one is not a solution. Then checking our work on the second one, for B, I would have that 7 equals negative 3 times 1 plus 10. That would be 7 equals 7. So it works for that one. Remember, it has to work in both equations, though. So if it works in the first one, we need to check the second one. The second equation is y equals 6 times the x value plus 1. 7 equals 7 there. That also works. And just to make sure we're on the right track, I'll double check it in C. In C, I would plug in 1 equals negative 3 times 3 plus 10. So that would be 1 equals 1. So that does work in the first equation. Now we check it in the second equation. 1 equals 6 times the x coordinate, which is 3 plus 1. That would be 1 equals 19, and that's where it doesn't work. So that work proves that B is the correct answer because it is the point that satisfies both equations. So we can see it on the graph, and we can see it algebraically. Let's look at our second example here. So for this example, we have the equations y equals x minus 1 and y equals x squared minus 5x plus 4. We can see that parabola for the x squared or quadratic equation, and we can say the line for the linear equation. Using what we just did, we are going to check all these again. So looking at point A here, if I plug in negative 3, so plugging it into this first equation here, I have y equals x value minus 1. That works. Let's check it in the second equation. So we would have negative 3 equals negative 2 squared is 4 minus 5 times negative 2 plus 4. And when I simplify that, I'd have negative 3 equals 4 plus 10 plus 4. And that would be negative 3 equals 18, which is not true. So A is not our solution. Let's check B now. So for B, if I plug in that y coordinate, I would have 0 equals 4 minus 1. That would be 0 equals 3 That is not the solution because 0 does not equal 3. So let's check C now. For C, my x-coordinate is 5, my y-coordinate is 4. So when I plug those in, I would have 4 equals 5 minus 1. That does work. Now we just need to make sure it works in the second one. So we have 4 equals 5 squared is 25. Minus 5 times 5 would be 25 also, plus 4. And that would be 4 equals 4. So C is our solution because we found the point that satisfies both equations in our system. So there's another question down here that says, are there any other points on the graph that satisfy both equations? So when we look at our graph, we can see that there's only one point where those two lines are the same. So there are no other points where those two lines are the same. So there are no other points to satisfy that equation. If we look at our second system, we know that this point at 5, 4 is a solution. And we can see from the graph that there is this other intersection point where the two graphs are the same. So we would say, yes, there is another point for this one. There are two intersection points, and the second one is at 1, 0. So based on what we've seen, the points of intersection represent the solutions to a system of equations. So when we have two or more equations, it makes a system, and their intersection points on the graph represent when they are the same. Okay, we're going to jump now into looking at some different types of systems. So we've kind of seen a little bit here. We're going to jump a little bit more into it. So on that next page, we are going to look first at linear to linear systems. So this is where our equations for our system are both linear equations, two lines. So for this first example, we can see those two lines on the graph, and remember we're looking for their intersection points. So those first two lines are never intersecting. So we would say those have no solution. And that happens because the lines never intersect. For lines to never intersect, they are parallel. So anytime we have two parallel lines, they're going to have no intersection. In the second one, we can see that those two lines intersect one time. So there is one solution to that system of equations. And that's because they intersect at one point. Our last linear to linear system that can happen is where those two lines are always intersecting. So it looks like one line, but it's because they're the same line as each other. When two lines are the same, we say that they're always intersecting, which means they have infinite solutions. Every point along the line is a solution. So those are linear to linear systems. Two lines, we're looking for their intersection point. Now we're going to look at linear to quadratic systems. So this is where we have a linear equation and a quadratic equation. We saw that in example B on the first page. In some situations, we will have graphs that have no solution. So that means that the line and the parabola never intersect. So an example of that would be like this. We have a line and we have a parabola, but they're never going to intersect each other. Parabola is going completely up away from the line. So those have no solution, no intersection point. The next one is where those two things are going to intersect one time and one time only. So an example of that would be like this. So the parabola and the line intersect once, but are never going to intersect again. And then finally, and most commonly, our parabolas and our lines are going to have two solutions. So they intersect two times. So that line is kind of going across the parabola and it's intersecting it twice. For Algebra 2, our last set of systems that we're going to solve are quadratic to quadratic. So this is where we have two quadratic equations and we're trying to see where they intersect. So two quadratics would be two parabolas on the same graph. If we want them to have no solution, that means they have to never intersect. So we need to draw those two parabolas in a way that they will never cross. In order for that to happen, one has to be facing up and one has to be facing downward. Occasionally, we will have two parabolas that will only intersect once, so they only have one solution. And when that happens, you will see parabolas that just touch at that one point and then go the other directions from each other. And finally, we'll have sometimes parabolas that intersect twice or have two solutions. So that would look something like this, where they have two intersection points and again are facing away from each other otherwise. There is the possibility that we could have two parabolas, just like we had two lines that are always intersecting. So we could have two parabolas that are exactly the same, and they would always be touching, just like the two lines up above in example 3 were. That would be infinite solutions. Lastly, today we are going to practice a little bit with these systems. So what I would encourage you to do here is pause the video and sketch the equations in these systems on the coordinate pairs that are provided, or coordinate planes that are provided, and then come back and check your work. So pause, graph those equations, come back when you're done. Okay, hopefully you've taken the chance to pause it and try these on your own. So our first system, number 1, is two linears. I have negative 3x plus 10 and 6x plus 1. If I graph those, they look like this. Negative 3x plus 10 is the blue line going downward. 6x plus 1 is the purple line going upward. And the intersection point on there where they cross each other is at 1, 7. So that would be my solution. This second set of equations here, we have, again, two linears, but they're not in a great way to graph. So hopefully you took an opportunity to rewrite them in a way that made them easier to graph. So this one would be 1/2 x minus 3. And the second one, I would have to rearrange it. When I rearrange it, I would start by adding the 8. So I would have x plus 8. And then dividing by 2, I would get 1/2 x plus 4. And when I graph those two, I get a graph that looks like this. And we can tell from both the equations and from the graph that those two lines are parallel to each other. So parallel slopes here, they have the same slope, and I can see that in the graph. And when two lines are parallel, they never intersect, so we say there is no solution. Let's look at number 3 and 4 now. For number 3, we have a quadratic and a linear. So you're going to graph that parabola, and then you're going to graph the straight line. When you do that, you get a graph that looks like this. And we are looking for their intersection points. I can find 2 here. There's one down to the left and one up to the right. Those intersection points are at 1, -3. And then that other one is at 4, -9. And lastly, we have another parabola with a linear function. So that parabola is in vertex form, so I can graph the vertex, go from there. When I graph that parabola in line, I get a graph that looks like this. And I can see that that intersection point that's highlighted there, it is only one intersection. That point is at -5, -4. So that system has one solution. All right, lastly today, we have the graphing calculator steps here. So these are for the TI-84. If you have a TI-84, you can follow the steps on the left-hand side, entering the equations in y1 and y2 when you do that. The first equation, you just enter in the y1. The second equation, you enter in y2. And again, when you enter those, they do need to be in y equals form. So you would have to rewrite each one in slope-intercept form, or if it's a y, or if it's a quadratic, you would still have to solve for y. So that second one would be y equals 2x squared plus 5x plus 1. So then you can enter them in y1 and y2, graph them, and see if you need to change the window at all to be able to see where they intersect. To find the intersection points, you hit second, trace, and then number 5 is intersect. So you find those intersections. You click on the first curve, whichever one, doesn't matter, and then click on the second curve and hit enter one last time, and it'll show you the intersection points. So again, I would encourage you, if you have the TI-84, to pause the video, practice these 4, write down your solutions, and then come back and check. So for this first one, the solutions were at -1, -2, and 0, 1. For number 6, those two never intersect, so they would have no solution. For number 7, those two parabolas intersect once at 0, 0. And number 8 has 2 intersection points. Those cross each other twice. So it would be -212 and 668. So you probably had to change your window a bit to get those. All right, that is graphing systems of equations. We'll see you next time.